I want to introduce a vector field. Now, a vector field is a vector in either 2 or 3 dimensions of the following form. It is a vector of functions. So a 2-dimensional vector field would represent a function of x and y, and in 3 dimensions, obviously, x, y, and z. We generally shorten it to this notation where it's implied that mn or mn and p are all functions of x, y, or x, y, and z. So a typical vector field in 2 dimensions might look something like this. E to the xy sine x plus cos y. Or in 3 dimensions, it might look like x squared z, z cubed, xy squared. Now, a vector field almost always represents a force vector. We will get into that a little bit later. So for now, we want to just introduce the concept. Now, a potential function is any function of either 2 variables or 3 variables that I'm going to use to generate a vector field. There's an infinite number of functions in 2 or 3 dimensions, but what makes something a potential function is that if I take the gradient of f, I will produce a vector, and that vector becomes the force vector. If I do the same thing in 3 dimensions, I get a 3-dimensional force vector. So a potential function is a function that produces the vector. Now, not all vectors come from functions. Those are very, very special cases. So if my force vector f comes from the gradient of f of x, y, then we say that f is conservative. As we will see, conservative forces are the most important types of forces and the most useful. So a simple example would be something like this. If f of xy, let's say, equals e to the xy plus x squared minus y cubed, simple function of 2 variables, then we would say my force vector, which is the gradient of f, would be the vector of partial derivatives. So the partial with respect to x, then the partial with respect to y. So this vector here we will identify as being a conservative vector.